Welcome to my virtual poster presentation. I'm Yu Chen from Cornell University, Department of Statistics and Data Science, and my advisor is David Madison. Today, I'm going to present my recent work on non-parametric ridge recovery of TEM image series given temporal parametrization. And this is an application within the field of material science. Transmission electron microscope images like the example on left has pixel values representing the number of electrons detected and accepted by the machine, and those darker spheres indicating places where atoms are stuck together to form atomic columns. The most common task of TEM images is to accurately extract the atomic columns locations and other features for follow-up analysis. However, with the severe signal-to-noise issues, one can hardly claim that there is an atomic column at certain locations, especially at the surface of the nanoparticles, which tends to be rather unstable. Additionally, there are also some frequent abnormal situations where those atomic columns can have irregular projected shapes, drifting centers, varying contrasts, and even occasionally degenerative cases as the constantly jumping atoms may lead to an absent atomic column. However, if we look instead at the video, one becomes much more certain to make a claim about atomic column locations. Furthermore, if we zoom into one specific atomic column and align them temporally, a tube or a cylinder is then formed, and this is exactly what a ridge would look like in a three-dimensional mapping. Hence, it motivates our ridge detection framework with the benefit of the flexible ridge structures, such as freely stretching curve and the arbitrary, sometimes even zero tube radius. Among TEM processing algorithms, Gaussian fitting methods are the most popular, but also most restrictive one concerning prior graphical assumptions. Examples include Tract from MATLAB and AtomMap from Python. In our earlier work, we introduced the classical blob detection algorithm to this specific field, and Andrew further developed the topological data analysis framework to handle this task. However, these algorithms still limit themselves to frame-by-frame object recognition, while here we propose the novel point of view to utilize the temporal correlatedness for analysis using ridge detection. Ridge detection is also a well-developed tool in classical computer vision and image processing. Some state-of-art algorithms are collected by the Python package skimage. However, most of these approaches are designed to reproduce a filtered visualization with intensified and enhanced ridge structures for future manual and visual inspections. Since our goal is to extract the information for future analysis, we propose differently a non-parametric setup to extract the ridge as a continuous function of time, so that at the later stage, the dynamics of the atomic columns can be explicitly expressed. For definition, a ridge of a three-dimensional mapping is a continuous collection of points where the mapping attains its maximum along two of the three principal directions, while it can vary arbitrarily along the remaining direction. For principal directions, I mean the eigenvectors of the Hessian matrix. In particular, here we generalize slightly to allow zero eigenvalues in order to account for the degenerated cases where the ridge shrink to a point with zero radius, which will happen when atoms are absent. And motivated by our TEM example where atomic columns are aligned temporally, we also assume that the ridge function has the main direction along the temporal axis. Hence, it can be expressed in such an analytical format as a function of time. We propose the intra-slice metric referring to three properties. One is that the ridge should be relatively stable spatially. Secondly, the gradient must be degenerated along two directions due to the definition of ridge. And finally, the curvature of the mapping projections indicating that the two latter eigenvalues should be non-positive and have comparably larger magnitudes than the remaining one. Finally, an intra-slice metric is aggregated with such local gradient and Hessian behaviors. And then here comes to the main novelty of this work. Since we want to express the ridge as a function of time, the implicit continuity restriction must be made explicit. And for two consecutive points P at time tau and Q at time tau plus 1, we interpolate them with cubic functions and measure the roughness as the integral of squared second-order derivatives. The smoothness metric can then be proposed and viewed as transition probability between the 2 points. Analogous to two-sided Markov process, we introduce the forward and backward metric to account for the accumulated transition probability from the very first and very last frame. Or recursively, the forward metric for P at time tau can be viewed as the propagation of forward metric from the previous temporal slice at tau minus 1 with corresponding transition probabilities and multiplied by the intra-slice metric. Finally, we assign the algebraic average of forward and backward metric as a pixel weight, which will be used at the next step. And to give the non-parametric estimate, we can use the pixel weight to calculate weighted average location and tangent for each slice, and hence the slice-specific linear functional element accordingly. The non-parametric ridge function can then be given by the classical form with kernel function k and bandwidth h. The choices of k and h are well studied in non-parametric literatures. With nanoparticle model in A, we simulate 10 frame noise realizations to the example clean TEM image B with static underlying structure and compare the performance of our algorithms with other milestones. We also implement our algorithms on the simulated 200 frame noisy video with dynamic patterns from the structures S1 to S3, which have essential differences at the atomic column 23 and 25. Concerning the performance on static structures, the box plot summary of errors in those three aspects suggests that the ridge detection algorithm is the most consistent and stable one among all other benchmarks. Switching to the 200 frame dynamic cases with state transitions, the Euclidean errors here also demonstrates the efficiency of the ridge detection algorithm. It is worth addressing that the unit is pixel, and since the images are naturally discretized into pixel grids, the overall perturbation ranges of Euclidean deviations for either the center column 16 or the surface columns 23 and 25 are all satisfactory to be below 1 unit for Euclidean distance. And finally, some conclusions. The ridge detection is a natural extension from blob detection, as aligning blobs temporally forms exactly the ridge in the three-dimensional case. Secondly, ridge detection maximally utilizes temporal information to recover the dynamics and trends of atomic columns movements, while it also maintains sufficient independence between frames other than smoothing out all local subtle features. By simulations, this ridge detection is outperforming other milestones, though with worst computational sacrifice for accuracy when including the continuity constraint. And finally, here are some references for the presentation. Thanks for listening.